Okay, welcome to the last section of chapter 13. Today we're talking about 13.5, which is solving trigonometric equations. So remember, in the past we've been verifying identities. That's different than solving a trigonometric equations. So we're going to be talking about how to solve those today, and also talking about the fact that sometimes there are extraneous solutions, just like there have been in other types of equations we've solved throughout the year. So far in this chapter, we've studied identities, which are a special kind of trig equation. Remember that trig identities are true for all values of the variable in the domain. In this section, we're going to talk about solving trig equations that are not identities. They're only true for certain values of the variable. Just like x plus 2 equals 3 is only true for x equals 1. It's not true for everything, right? So we're going to be looking at trig equations that are not identities, but they are just equations to solve that will only have certain values of theta that make them true. This is just like solving algebraic equations. We'll be factoring, adding and subtracting to both sides, things like that. All right, so let's look at this first example. Here I have 2 cosine squared of theta minus 1 equals sine of theta, and theta is only going to be in the first 2 quadrants. Okay, so we are still going to use identities sometimes to replace parts of an equation that I need in order to be able to solve it algebraically. So in this case, I notice I have cosine and sine. Right now that's going to make it hard to solve because I have 2 different trig functions in this equation. So notice what they do. We replaced cosine squared of theta with 1 minus sine squared of theta. So I just replaced cosine squared with 1 minus sine squared. Why is that helpful? Because now everything is in terms of sine. So I'm going to distribute the 2. So 2 minus 2 sine squared of theta minus 1. We move the sine squared of the sine of theta, over to the left side so that everything is equal to 0. And then we're going to simplify. So I have negative 2 times sine squared of theta. 2 minus 1 gave me the plus 1, and I have minus the sine of theta. You should think of this as looking like negative 2x squared minus x plus 1 equals 0. This should look to you like a quadratic function, just instead of x we have the sine of theta. So we're going to divide each side by negative 1 to make my leading coefficient positive, because that's going to make my factoring much easier. So again, this is like having 2x squared plus x minus 1 equals 0. If you think about it like that, it's going to make factoring it much easier. So notice how they factored it here. 2 sine of theta minus 1 times sine of theta plus 1. Again, that's like having 2x minus 1 times x plus 1. You're just thinking of your x as being sine of theta. You should remember how to factor that. 2 times negative 1 is negative 2, so 2 numbers that multiply to negative 2 and add up to 1, and then you do grouping. Okay, I'm not going to go through all of that right now because you should already know how to do that. So after I factor, now I can use the zero product property. So I set each factor equal to 0. 2 times the sine of theta minus 1 equals 0. That means that the sine of theta has to equal 1/2, so I'm isolating the sine of theta. And so I don't know what's happening here. Where is the sine of theta equal to 1/2 in the first 2 quadrants? At 30 degrees and at 150 degrees. So those are the 2 values of theta that work for that factor. 30 degrees and 150 degrees. Oh, sorry, now I see what they were doing on this side. This is my other factor, sine of theta plus 1 equals 0. So sine of theta equals negative 1. Where is the sine of theta negative 1? At 270 degrees. But our original problem told us that we're only taking theta from 0 to 180 degrees. So my only solutions are 30 degrees and 150 degrees. I don't include the 270. Okay, so you guys try this one. Your answer here is D, 0 degrees, 90 degrees, and 270 degrees. All right, and here is the work. So notice, first of all, I have 2 terms that have cosine and 1 with sine, so I'm going to try to write everything in terms of cosine. So I rewrote sine squared of theta as 1 minus cosine squared. And then this cosine with the 2 theta inside, that can be hard because I can't really get to that 2. But because of the double angle identities from the last section, I know I can replace cosine of 2 theta with 2 cosine squared of theta minus 1. So now I have cosine squared and cosine. So when I simplify that, I get 1 cosine squared minus 1 cosine squared of theta minus cosine of theta equals 0. Factor out a cosine of theta, so I have cosine of theta times cosine of theta minus 1, and I set each factor equal to 0. So where is cosine of theta equal to 0? At 90 degrees and 270. Where is cosine of theta equal to 1? At 0 and at 370. I think since they said it included 360 degrees here, that 360 degrees should also be part of your answer. All right, let's take a look at this second example. Sometimes when I solve a trigonometric equation, I will have infinitely many solutions. That happens a lot of times when it says for all values of theta. So it's not restricting me to a certain range of theta or domain of theta. So let's take a look at what we do here. I have the cosine of theta plus 1/4 equals sine squared of theta. Cosine minus sine squared of theta equals negative 1/4. And in this case, they're having us look at the graph to solve it. So what you would do is you would graph this part, cosine of theta minus sine squared of theta, and look for where it equals negative 1/4. I'm going to show you that on Desmos real quick. So notice here, I'm graphing cosine of x minus sine of x squared, or sine squared of x. Make sure when you're in Desmos doing this, if you're doing it in degrees, that you click over here into degrees. And notice I made my x-axis go from negative 360 to positive 360, and my y-axis I reduced from negative 1.5 to positive 1.5, just to zoom in on the right part of the graph. And then what I'm asking is, where is this equal to negative 1/4, or negative 0.25? So I graph that line, and I'm looking for the intersection of these two things, right? I could also have put in this as y equals. So where do they intersect? They intersect at negative 300 degrees, negative 60 degrees, 60 degrees, 300 degrees, and so on. This will go on forever and ever, right? It's infinite. And so that's what they say over here when they're showing you on the graph. The solutions are 60 degrees, 300 degrees, and so on, which we saw from the graph we just looked at. And the period of this function is 360 degrees, which you can also see from the graph. Desmos is super helpful for this. So since there's infinitely many solutions, I have to find a way to write them in general. So we say 60 degrees plus k times 360 degrees. What does that mean? It means that every 360 degrees, it's going to be repeat. And we should say here that k is an integer, right? So if we look back at our Desmos graph, at 60, and then again at 60 plus 360 over here, which is 420, I would have another solution, right? Every 360 degrees, I get that same solution again. Same thing with 300. I start at 300, it's equal to negative 1/4. Then again at 300 plus 360, so at 660, it's equal to negative 1/4, and so on. So I write my general solutions as 60 degrees plus all of the multiples of 360, and 300 degrees plus the multiples of 360. And since k could be an integer, positive or negative, it can go in either direction. All right, let's take a look at this one, where I'm measuring in radians. 2 cosine of theta equals negative 1. I'm looking for where the cosine of theta is negative 1/2. There's two ways to solve this one. We can look at the graph, or we can also think about the unit circle. Where is the cosine of theta equal to negative 1/2? Well, we know that the cosine is negative in the second quadrant and in the third quadrant, right? So where does the cosine equal 1/2 or negative 1/2 in those quadrants? From special right triangles, we know that the cosine of 60 degrees, or pi over 3, is 1/2. So it's wherever I have a reference angle of 60 degrees. So if I think about my quadrants, where do I have a reference angle of 60 degrees? Well, this angle here would be, so it would be 120 degrees. And if I'm thinking about the angle in this quadrant that has a reference angle of 60 degrees, it's 180 plus 60, so 240 degrees. But of course, they're asking us to talk about this in radians. So we would say 2 pi over 3 and 4 pi over 3, but it would go on forever and ever, as we can see from the graph, because we're talking about all values of theta. So I would have 2 pi over 3 and 4 pi over 3. The period is 2 pi, right, when I'm talking about radians. So every 2 pi radians it repeats. So here I have k, representing my integer multiple, times 2 pi. So 2 pi over 3 plus 1 2 pi, or 2 2 pi's, or 3 2 pi's, or negative 5 2 pi's. I'm still going to get to a place where 2 times the cosine of theta equals negative 1. All right, try this one. Okay, your answer here should have been D, 90 degrees plus all of the multiples of 360. All right, we're running a little bit out of time, so we're going to skip from example 3 and go to example 4, and we're going to talk about extraneous solutions. Some trig equations might have no solution. For example, if I'm asking you, what values can I plug into cosine to get 4? We know that's impossible because cosine only goes from negative 1 to positive 1, right? It can't go to 4. So this would have an empty set. Sometimes another thing that can happen is I can solve, and when I plug something in, it may or may not work. So let's take a look at example 4 here. I'm going to solve this equation. Cosine of theta equals 1 minus sine of theta. It's my original equation. I'm going to square both sides. So I end up with cosine squared equals 1 minus sine of theta, quantity squared, right? So I have to think about that means 1 minus sine of theta times 1 minus sine of theta. So I have to FOIL it out. And notice we replace cosine squared with 1 minus sine squared. That's one of the reasons we squared both sides, is to be able to replace some things with identities and then be able to factor. So I move everything to the right side and simplify. So I end up with 2 times sine squared of theta minus 2 sine of theta, factor out a sine of theta, and set each factor equal to 0. So where is the sine of theta equal to 0? Where is 2 sine of theta minus 2 equal to 0? When I simplify this and solve for sine of theta, I get sine of theta equals 1. I know that sine of theta is equal to 0 at 0 degrees, 180 degrees, or 360 degrees in this interval that they give me. Where is sine of theta equal to 1? At 90 degrees. Then what they're showing us here is we're just checking our different values. Let me pull up everything here for you. So when I check when I check 0 degrees, it works. I get 1 equals 1. When I check 180 degrees, though, I get negative 1 equals positive 1, which is not true. When I check 90 degrees, it works, and when I check 360 degrees, that also works. So notice I had one extraneous solution, which was 180 degrees. All right, try this one. Okay, your answer here is A. And here's the work for this one. I notice I get everything equal to 0. Then I factored out a sine. So I get sine of theta equals 0, which in this interval would be at 0 degrees or 180 degrees. And then I get 0 equals sine of theta minus cosine of theta, which means that sine of theta has to equal cosine of theta. Where are sine and cosine equal? Well, we know at 45 degrees in the first quadrant, both sine and cosine are equal, square root of 2 over 2. And also in the third quadrant, where sine and cosine are both negative, square root of 2 over 2 at 225 degrees. So here I end up with 4 solutions. I'm not showing you the check right now, but you should make sure to check them in the original to prove that they all work. All right, last example, super quick. If I can't solve easily by factoring, and we've kind of already talked about this, you try using identities. But this is why it's so important to check. Because if I'm using identities, or if I'm like squaring both sides, a lot of times you get an extra or an extraneous solution that doesn't work. So take a look at this example real quick. Here we have the tangent to the fourth of theta minus 4 secant squared of theta equals negative 7. Oops, sorry. So take a look at what they've done here. Replacing secant squared with 1 plus tangent squared. This is quadratic in form. This is tangent squared squared minus 4 tangent squared plus 3. So I can factor it in quadratic form and then use my zero product property. You might want to pause to take a look at this for a second longer. And when I solve, I end up with a bunch of solutions. This is for all values of theta. And so I have to write them out using the